Good afternoon. Let's continue our discussion about properties of plane wave in dielectric and conductors. This morning, we just finished case 1 and case 2. So now, let's discuss case 3. We are going to talk about waves at optical frequency, maybe high frequency, and beyond. Consider case 3.1. This is a generalized dielectric constant. Omega is greater than gamma zero. So imaginary part plays a very important role. We have minus I here, we have I here. So therefore, this part is real. That's very interesting. This part is real. Conductor becomes real, but negative. Okay, how about bond charge? Bond charge omega j is greater than omega. Omega j is greater than omega. So epsilon B is still a bond charge. For all or some of the bound electrons. So from this equation, this part is still complex, but epsilon B is complex. And this part becomes purely negative. The free electron terms is predominantly imaginary. When omega is smaller than gamma zero, omega is small, that's purely imaginary. But in this case, omega is much greater than gamma zero. It becomes predominantly real. A quantity departure from case 2, okay, is real but negative. This radically changes the metal response to EM waves. Examples are given below in case 3.2. So the interesting part is this one becomes real and negative. What happened if omega B is smaller than this one? That will be very, very interesting. Okay, move on. Case 3.2. Let's consider this case again. Omega is greater than omega j. Omega is greater than omega j. This one, gamma j, and greater than this one for all electrons in the medium. So in this case, omega is very, very large, and omega is much, much larger. So we have a m in a denominator, n in the denominator. Here is omega squared. We have minus omega squared. I cancel, so we have a minus sign here. NFJ, sum over OJ, NF0. So this one consider all the charges. Atomic numbers. G is all the charges. Nz is the density of all electrons bound and free in the medium. So this part becomes very easy. Minus Nz E squared over m omega squared. Okay, so epsilon divided by epsilon 0 is 1 minus omega p squared over omega squared. That will be less than 1. Less than 1. So for plasma, these terms will be less than 1. Interesting. So we create a condition. Epsilon is less than 1. Mu can be less than 1. Okay? Epsilon is less than epsilon 0. Okay? So omega p squared equals Nz E squared over m epsilon 0. Ng is the density of all electrons in the medium. Okay, we finish the first case 3. Let's move forward to case 4. Case 4 is the waves in plasma. What is plasma? Plasma is a partially ionized, such as, for example, ionosphere, or fully ionized, for example, fusion plasma gas. So plasma is a partial ionized or fully ionized gas. In general, effects of neutral gas, if present, and collisions can both be neglected. The effect of neutral gas and collision can be neglected. Ion motion can also be neglected at sufficient high frequency because ions are quite heavy as compared with electrons. So their motion is relatively slow. Okay, so in this part, that's neutral gas. You can negligible, small, and this one we have gamma 0 approach 0. Why? We have positive ion, we have positive charge, negative charge, but why is gamma equals 0? Because for plasma, the density, the vacuum is relatively low. So collision is low as compared with the frequency. So as compared with the frequency, therefore Ne squared over F0, we have this one. And you can omit this part. Just keep this part. And this part becomes negative. So for plasma, looks similar to case 3.2. Same equation at 7.59, but with a much smaller omega p, 7.59. Let's go back. This one. Okay, same equation, but the value is much more smaller. Okay, omega p is the plasma frequency, defined as Ne squared over epsilon 0 n. So n is the plasma electron density, normally much smaller than the density of the solid. So because free charge is relatively small as compared with total charge, atomic number, so this part is small. Okay, therefore plasma frequency is normally relatively small. It's number density. Okay, so epsilon once again is less than epsilon 0. Substitute epsilon to here. We obtain k squared equals mu epsilon omega squared equal mu 0 epsilon 0. Okay, you just factor out mu 0 epsilon 0. So here it's 1 over c squared and omega squared here, omega p squared here. So that's the equation. Now 1 over c squared can multiply here. So we have k squared c squared, and we have omega squared. And we have another one, this one, here becomes here, omega p squared. So omega squared equals k squared c squared plus omega p squared. It's a dispersion relation between omega and k. If we draw a figure, it looks like this one. Omega p will be the cutoff frequency. Below this frequency, k will become imaginary, purely imaginary. Above this frequency, k will become positive or negative. Positive k means forward wave, negative k means backward wave. Equation 37 is the well-known dispersion relation for EM wave in a plasma in the absence of external applied static magnetic field. Consider section 7.6, consider the dispersion relation for a magnetized plasma. When omega is extremely large, all material has a dispersion relation given by this one. But for the plasma, it's valid for all frequency. Okay, pretty good. That's the end.